Hello everyone, welcome to week number 7 where we are going to talk about the vapor power cycles. Over last 3 weeks we have talked about the power cycles only, but where the working medium was some kind of non-condensable gases. Like in week number 4 we talked about the ideal cycles for reciprocating type internal combustion engines, where or I should say which are the generally working cycles for all the automobile vehicles, cycles like the Otto cycle or diesel cycle or dual cycle, and also in conjunction to that we have discussed about the Stirling and Ericsson cycles also. In week number 5 we focused more on some practical aspects related to those ideal cycles, and in the previous week we have talked about another gas power cycle which was associated not with reciprocating engines but more with rotary type of engines, that is the gas turbine. So, we have talked about the Brayton cycle there. Now, in both these two kinds of cycles, that is the Otto or diesel group of cycles and the Brayton cycle, the common working factor was we worked with one non-condensable gas, that is the working temperature limit for the working medium over the entire range of operation over the entire span of the cycle remains well above the critical point. In no way it can come anywhere close to the critical point, thereby completely eliminating the possibility of any kind of phase change, and hence we dealt only with the gaseous medium. However, in practical situations quite often we have to go for power cycles which involve some kind of phase change, commonly a liquid to vapor and vapor to liquid phase change, and corresponding cycles are the ones that we are going to discuss in this particular week under this title of vapor power cycles. Now, this is something that I have shown earlier also in the last week only, where we have classified the heat engines into two broad categories, the IC or internal combustion engines and the external combustion engines. And there under IC engine we can have both rotary and reciprocating version, same in case of EC engines as well. Now, under the reciprocating category, the gasoline engine or so called the spark ignition or SI engines and the diesel engine or so called the CI engines are the ones that we have already discussed. We have already discussed about this particular cycle. From the diagram, can you identify? I am showing the TS diagram only, but you can clearly see here we have two processes which have constant volume which are constant volume in nature, and two processes which are isentropic in nature. Then which cycle is this? Yeah, you got it correctly. This is the Otto cycle, where we have constant volume heat addition and constant volume heat rejection and isentropic expansion and isentropic compression processes. So, this is the Otto cycle, which is the ideal cycle for gasoline based reciprocating IC engines or the SI engines. Whereas, which cycle is this? Here we have heat addition at constant pressure and heat rejection at constant volume and two isentropic processes. Definitely this is the engine or cycle corresponding to a diesel cycle or diesel engines. We call it a diesel cycle, which is the ideal cycle for diesel engines or the CI engines. We have already discussed about them. In the previous week we have discussed about this particular cycle. Just look at it, I am sure you will be able to identify it. Here we have two constant pressure processes and two isentropic processes, both heat rejection and heat addition are at constant pressure, and therefore, this is the Brayton cycle, which is the ideal cycle for both open cycle type gas turbine and closed cycle type gas turbine. In open cycle type gas turbine, we work with the IC engine mode only, where the combustor remains inside the engine cylinder, whereas in case of closed cycle type gas turbine, we work more in external combustion mode, where instead of having a real combustion, actually we work with a gas which receives energy from some external source. Both open and closed cycle type gas turbines have practical applications. In this week, we are going to talk about this particular one. Steam engines are obsolete nowadays, so there is no point discussing about them, but steam turbine is, you can say, is the prime mover of the modern industry, because most part of the commercial power that you use for various purposes throughout the world, at least 50 to 60% of that comes from steam based power stations, and if we include the nuclear stations which actually produces the power again in the form of steam based power stations, so it can well go into the range of 75%. So, we have to discuss about the ideal cycle for steam turbines in this particular week, but before that we are quickly going to revisit the Brayton cycle. And this is the Brayton cycle. We have shown the diagram in the closed cycle mode. So, what we have here? We have a compressor where the working medium, which is a gas, that gets compressed from some low pressure at P1 to high pressure at P2. Then we have a heat exchanger where energy is supplied from some external source. Remember, this closed cycle is an external combustion type engine. So, here we do not have any combustion, rather heat is getting supplied from some external source. This Q in is coming from some external source, and that gets added to the gas working medium in the heat exchanger, thereby raising its temperature from T2 to T3. Then in the turbine it goes for the expansion process, the isentropic expansion, from where we get the real work output. So, it comes back to the lower pressure level at pressure at point 4, and then it rejects the waste heat in the form of Q out in the second heat exchanger, so that it can go back to stage number 1. This is the corresponding PV diagram, and this is the TS representation, which I have also shown in the previous slide. So, here we have 1 to 2 as a constant entropy, or I should say isentropic type compression process, during which the pressure increases from some, say we can talk about say a low pressure and a high pressure level. So, it works, or the pressure increase in the compressor from this low pressure level at state 1 to the high pressure level at state 2. Then the ideal heat exchanger where there is no pressure drop, and its temperature increases from 2 to 3. We can see from the TS diagram, this is the temperature at the end of compression process, where it increases up to this particular level. This is the temperature at the end of heat addition process. So, a significant increase in the temperature at constant pressure. Then we have the expansion process from 3 to 4, during which entropy remains constant, because it is a frictionless adiabatic process in ideal situation. So, it falls back to the low pressure level. Then we have the heat rejection. Now, we have already discussed about the ways to improve the performance of this in the form of intercooling or reheating or regeneration. There is no point going for that. We are just sticking to the basic ideal Brayton cycle. We know how to identify the work output from this cycle, how to estimate its efficiency, etc. But one big concern that we have with this Brayton cycle is the temperature at the end of the expansion process, at the end of the turbine expansion, that is at this point number 4, that is still significantly higher compared to the atmospheric temperature. And therefore, even when we are working in the ideal cycle mode, there is no point we should let it go to the atmosphere. Definitely we can go for regeneration to improve the cycle performance, and then only we can reject, or sorry, I should say we can reduce the amount of heat rejection. But another problem that we can't avoid even when we are using all of those intercooling, reheating and regeneration is the back work. Here the back work corresponds to the work required by the compressor, and as we are compressing a gas in the compressor, we already know the compression work required here is equal to integral minus VdP, because this is an open cycle rotary kind of device from point 1 to 2. And as we are working with a gaseous medium, the specific volume is very high, and therefore, the compression work is also significantly higher. So, such that even as much as 30, 40 or 50% of the work produced by the turbine can be eaten up by the compressor. Even when you are using the intercooling, the back work ratio can be in the range of 30 to 40%, so which is a very significant number. Then what is the way we can reduce this compression work? Only possibility is that for a given pressure range, of course, only possibility is that if we can somehow reduce the specific volume of the working medium. That is precisely what is done by virtue of the intercooling, where we try to cool the gas to slightly lower temperature, so that its specific volume reduces. But instead of working with a gas, if we can work with a liquid, then we can get a drastic reduction in the specific volume, thereby causing a significant reduction in the value of this compression work, and hence even if the turbine work remains the same, there will be substantial increase in the net output that we should get from the cycle, and that is precisely what motivates us to go for the vapor power cycle, where though the expansion is done with a gaseous working medium, the compression is done with a liquid working medium, and in between the heat addition and heat rejection stages, that is where we get the phase change process, and that leads us to the ideal cycles for vapor based systems. Before going into the detail of the cycle, just look what we have. Here the heat addition and heat reaction processes are where we have some kind of phase change. If I just stick back to the Brayton cycle diagram, just in context with that I would like to explain again. Here the process 3 to 4, the expansion process that is shown, that will be continued to be done with a vapor, because the turbine work is also is equal to integral VdP, and here we want the specific volume to be high to get higher work output. So, we shall be using a gaseous medium, and that also we want this gaseous medium to be at a temperature as high as possible. But this compression part, that we shall be doing with a liquid, so that we shall be having a smaller specific volume and we can reduce the compression work. So, we may have similar level of turbine work, but we can have a significant reduction in the compression work. Therefore, the net work output from the cycle, that is Wt minus Wc, will have a substantial increase. And these two process, the heat addition process 2 to 3 and the heat reaction process 4 to 1, this is where we shall be going for some kind of phase change, so that we can have gaseous phase during expansion and liquid phase during compression. And correspondingly, the Breton cycle leads to the ideal cycle for vapor based power generation, which is called the Rankine cycle, based upon the name of William Rankine. Rankine cycle can be viewed to be just the phase change version of the Breton cycle, where we still have two isentropic processes and two isobaric processes. However, instead of working always with a gaseous medium, we shall be working with a phase change medium, so that the expansion part is done with a gaseous substance, the compression part is done with the liquid phase of the same substance, and both heat addition and heat reaction at constant pressures, they will be associated with phase change. But before we move on to the Rankine cycle, we should talk about the most ideal possible cycle, which is the Carnot cycle. Now, and this is the Carnot version of the vapor power cycle. Here 1 to 2 is the heat addition process. You can see here the black line, this particular line represents the phase vapor dome. We have talked in week number 3 about the properties of pure substances, and there you are introduced to this phase change process. We know that this particular line is known as saturated liquid line, this particular line is known as the saturated vapor line, and this is the point where they meet. This point is called the critical point. On this side of the saturated liquid line, we call the state to be compressed liquid or subcooled liquid. This side we call it to be superheated vapor, and inside the dome we have a saturated liquid vapor mixture. So, the state 1 is lying on the saturated liquid line. So, here state is of saturated liquid, here we are adding heat, and heat addition is done such that at the end of the process we reach state 2, which is of saturated vapor. So, during this particular process we are having a change of phase from purely liquid to purely vapor. Then if we and during this entire process both pressure and temperature remain same. Remember, during the phase change process, pressure and temperature are functions of each other. So, if one remains constant, the other also has to remain constant. So, though the Carnot cycle corresponds to two isothermal and two isentropic processes, here the isothermal processes are also isobaric in nature. Then the total amount of heat that you have added Q in corresponds to the change in phase from state 1 to state 2. Then if we neglect the energy, or okay, if we can therefore write this to be equal to E2 minus E1, assuming there is no work transfer associated with this, and if the changes in kinetic and potential energies are neglected, then this E2 minus E1 can be written as H2 minus H1, the changes in enthalpy, because you know that E is a summation of enthalpy plus internal energy plus enthalpy plus kinetic energy plus potential energy for a flowing fluid. And if the changes in kinetic and potential energies are negligible, which is a very good assumption to consider, then it gives to H2 minus H1. Similarly, process 3 to 4, this is the heat reaction process. Again we are having phase change going on. During 2 to 3 we are having isentropic expansion in the turbine. So, the system starts from point 2 at saturated vapor state, and as it expands in the turbine it gets converted to a liquid vapor mixture, ending up with point 3, which is having significantly high vapor content. Then we have the heat reaction between 3 to 4. So, we are having Q in during this process, we are having say Q out during this process. This is the process during which we are going to get the work production in the turbine, and this is the process of compression, where we are pressurizing, we are giving work input to this. I should put the arrows properly. Here work is given input to the system. So, the Q out in this case can be written as E3 minus E4, and again if we neglect the changes in kinetic and potential energies, then this reduces to H3 minus H4. How much will be the turbine work? Very simple, the turbine work will be equal to H2 minus H1, H2 minus H3. I have written correctly but told the wrong thing. We are assuming this process to be frictionless and adiabatic, so no heat transfer, no irreversible losses. So, the work output that we can get, that is just the simple difference in the enthalpies, and the compression work requirement similarly will be equal to H1 minus H4. And the point number 3 and 4 also can be easily identified, as these processes are isentropic in nature. So, we should have H2 equal to S3, and what should be your S3? We have done this in one of the earlier modules. I am just repeating the same thing. S3 should be equal to SF corresponding to the condensation pressure plus X3 into SFG corresponding to the condensation pressure. The same way we can calculate S4 or X4 I should say, because we know that as the compression process is isentropic. So, S1 should be equal to S4. This is the ideal cycle for a vapor power cycle in the form of a Carnot cycle. We can easily calculate all the associated work interaction and heat interaction. And what will be the efficiency for this cycle? Efficiency for Carnot cycle, we know this is the temperature, highest temperature of the cycle, which can be written as TH. This is the lowest temperature of the cycle, that is TL. So, the efficiency for this Carnot cycle will be equal to 1 minus TL upon TH. And depending upon the level of pressure at boiler and condenser, that is the temperature TL and TH, we can easily get any value of efficiency. So, it seems very simple, and then why should not we go for this? Because this cycle is practically impossible to achieve. There are several reasons. As we are going for the phase change process, so we are restricted to the maximum temperature. In order to ensure this liquid to vapor and vapor to liquid phase change, the maximum temperature, this TH, has to be lower than the critical temperature, has to be lower than this particular limit. And for a Carnot cycle, we know higher the value of TH, higher is the efficiency for the cycle. As here we are restricted by this critical temperature of the substance, then we are also restricted by the maximum possible level of efficiency that we can achieve. That is a serious concern, and not only for Carnot cycle, for any kind of vapor power cycle. Isothermal heat transfer at single phase is difficult. As long as we are doing within the vapor dome, that is, as long as we are having the phase change based heat transfer, both pressure and temperature remains constant, and it is quite easy to achieve in practice. But as soon as we enter this side of the dome or this side of the dome, we are into the single phase side. While it is quite easy to have constant pressure heat addition or heat reaction, it is nearly impossible in practice to have isothermal heat transfer, and that is another big concern about having this Carnot cycle in practice. Low steam quality at the turbine exit. As we are starting with a saturated vapor at the beginning of the turbine expansion process, then this point number 3 will have significantly large amount of vapor content. This quality X3 at this point can easily be in the range of 70 to 80%, which is significantly low compared to the practical levels. In fact, as the quality at point number 3 keeps on dropping, there will be more and more liquid droplets that keeps on appearing in the mixture of liquid and vapor at point number 3 or towards the later stages of the turbine expansion. And as the mixture passes at a very high velocity through the turbine, so these droplets can strike the turbine blades with very high velocity, causing erosion wear to the turbine blades, which is quite significant. And therefore, there is some kind of practical limits. In practice, we never want this quality at this point X3 to be less than 0.88 or 88%. We never want this, or I should say we always want this X3 to remain greater than 0.88. That is some kind of practical operation based limits, and that is quite difficult to have in Carnot cycle based operations. One way of doing this, if we can identify some fluids for which the saturated vapor line is quite steep, that is having instead of having the line the way it is shown, if the line is somewhat like this, then maybe we can have this expansion process with significantly high value of X3, but finding such a liquid may not also be so easy. Another problem, difficult to stop the condensation precisely at this state point 4. As we are having the phase change going on, stopping at a particular quality value again has required significant control operations and still may not be very much possible. And another big problem is with the compression from 4 to 1. At point number 4, we are having a mixture, a low quality liquid vapor mixture. At point number 1, we have saturated liquid. So, as we are compressing this mixture, the liquid content keeps on increasing. There is a phase change going on. That is very difficult. Compression of the mixture is practically impossible to control and impossible to achieve. And that is the reason that this Carnot cycle is not the most practical one to have for large scale power generation in practice. Another problem that we shall be demonstrating through a numerical example shortly, that Carnot cycle, though it gives very high efficiency, corresponding work output will also be significantly low. We shall be seeing that shortly. One way we could have achieved this cycle is by shifting the entire thing towards higher temperature limit, something like this, where we are having phase change going on for the condensation, but there is no phase change in the boiling part. In the heat addition part, here we are having heat addition in the supercritical stage. Point number, this particular temperature level is well above the critical temperature. So, we are somehow taking care of this particular limit, and the heat addition is taking place at supercritical level, though heat rejection is still within this phase change dome. There is still phase change involved with heat rejection. But one problem with this, we have to compress to extremely high pressure. The pressure at point number 1 can be much larger than pressure at point number 4. So, designing such a compressor is very difficult, and isothermal heat transfer that is happening from point 1 to 2, that is happening now at variable pressure, because as we are moving from this direction to this direction, the pressure also keeps on changing. Now, designing a heat exchanger where temperature will remain constant, but pressure will keep on varying, again that causes lots of practical difficulty. So, the Carnot cycle based vapor power cycles, though seems very easy to have in from theoretical considerations, are a no kind of situation in practice. Then what we should go for? We just modify this Carnot cycle slightly to attain the Rankine cycle that I mentioned. We go more like the Breton cycle mode, that is, we shall be retaining the isentropic expansion in the turbine and isentropic compression, but instead of having isothermal heat addition and heat rejection, we shall be having isobaric heat addition and heat rejection. That is, this is the arrangement where we do this. Here we have a pump. In the pump, the system pressure is increased from some level P1 to P2, and that is done using some kind of liquid as the working medium. So, this 1 to 2, our working medium is a liquid. At point number 2, we are having a high pressure liquid, then it passes through the boiler, and within the boiler it goes through the phase change process. So, as it is passing through the boiler, we are having a liquid to vapor phase change, which conventionally we called evaporation. So, instead of boiler, the term evaporator is also quite commonly used. Then at point number 3, we can get several possible states. It may be a saturated vapor or it may be a superheated vapor. So, point number 3, our state may be saturated vapor or it can be superheated vapor. Then it passes through the turbine. From it is already at a high pressure level because of the action of the pump. So, entire boiler is at the high pressure level, that is from this point 2 this point 3, this entire thing is at high pressure. Ideal situation, we assume no pressure loss. So, P2 and P3 are equal to each other. Then in the turbine we have the pressure loss, which leads to the work production. P1 and P4 are again equal to each other, and this state of the system or working substance as state number 4 can be of saturated vapor or it may be a high quality mixture. So, at state number 4, we are having either a saturated vapor or we are having a high quality mixture, and then it passes to the condenser, where it condenses, heat is rejected, and during this process here we have the condensation. So, at the end of the condensation process, that saturated vapor or high quality mixture that we had at the end of expansion gets converted to generally saturated liquid. So, we have saturated liquid which goes back to the pump. Now, look here, the work input is given to the pump, but here work is done on a liquid. So, you can expect this work input to be extremely small. However, the expansion is done in the turbine where we are using saturated or superheated vapor. So, we can expect the work output to be quite large, and therefore, the net output, that is the turbine work minus compression work or pump work, can also be significantly small, or at least we can expect that the net work output should be the turbine work minus the pump work, and Q in is the amount of heat that is added to the boiler. So, we shall be using the symbol Q B from now to indicate this is the boiler heat addition. Q out is the amount of heat rejected in the condenser. So, we shall be calling it Q C. So, the net heat interaction over this cycle, cyclic integral of del Q, following the convention of first law of thermodynamics, we call it to be Q B minus Q C, because heat added to the system is positive. So, Q B is positive, Q C is negative, and net work interaction is the turbine work minus the pump work, which is your W net, because as per our convention the work done by the system is positive. So, turbine work is positive, pump work is negative, and as we are talking about a full cycle. So, this cyclic integral of del Q should be equal to the cyclic integral of del W. So, if we want to calculate the efficiency for this cycle, then the thermal efficiency for this cycle should be equal to the net work output by the amount of heat given to the boiler, that is equal to, we can write this either as 1 minus Q C upon Q B, or we can write this as W T minus W P upon Q B, whichever is comfortable to us. This is the T S diagram of whatever we have discussed. Point or process 1 to 2 is done in the pump, which is isentropic in nature, and it concerns a liquid. Generally, point number 1 corresponds to a saturated liquid state, this particular one, and here heat is given. So, point number 2 is subcooled liquid, but at a higher pressure. Then here work input is given between this 1 to 2. Then 2 to 3 is the heat addition process in the boiler. It can pass through several states, the system, like 2 to this particular point it is liquid, then here to this is where we have the phase change going on, and then up to point 3 we have the superheated vapor heating. Then 3 to 4 is the expansion, isentropic expansion for ideal turbine, and 4 to 1 is the compression. Now, depending upon the exit state from the boiler, where we can have either superheated or saturated vapor, we can have two kinds of Rankine cycles. First, we start with the basic one, which is the Rankine cycle using wet steam. Here the point number 1 corresponds to a saturated vapor. That is why we are calling it a wet steam, because the system is not allowed to go to the superheated level. We are always staying within the saturated vapor limit. We are putting a few assumptions. Firstly, we are assuming it to be steady flow process, and we are neglecting any kind of possible heat loss from during the boiling and condensation processes. We are assuming the changes in kinetic and potential energies to be negligible, and the liquid phase is assumed to be incompressible. The liquid phase that we are dealing with in the pump are assumed to be incompressible. So, if we talk about the first law of thermodynamics for an open system, then what we know? We know that for an infinitesimal open process related to an open system, we can always write del Q minus del W should be equal to dH plus d of kinetic energies plus d of potential energies. That is the total, the net of heat and work interaction should be equal to the summation of changes in enthalpy, kinetic and potential energies. Now, as per our assumption, these two are negligible, and so it becomes equal to dH. Now, let us go from one process to another or go through each of the processes separately. Process 451 is done inside the boiler. So, first we have the boiler which corresponds to the process 451. If we apply it on this, then Q 451 minus W 451 should be equal to H 1 minus H 4. Now, as this process is done inside a heat exchanger which we are calling a boiler or evaporator, here the work interaction can be neglected, or we can write this W 451 to be equal to 0 and Q 451, here heat is given into the system which is positive. So, this should be equal to QB. So, we have QB to be equal to H 1 minus H 4. Now, the turbine, the isentropic expansion that is happening inside the turbine via process 1 to 2. So, Q 1 to 2 minus W 1 2 should be equal to H 2 minus H 1. Now, it is an isentropic expansion. So, the heat interaction during process 1 to 2 is equal to 0 and the work interaction, it is turbine work, it is positive because work is given by the system. So, we can write minus W t is equal to H 2 minus H 1, that is W t is equal to H 1 minus H 2. Now, we go to the condensation process, the condenser process 2 to 3. So, following the same pattern, we are writing Q 2 3 minus W 2 3 is equal to H 3 minus H 2. Again, this is heat is rejected during this process and we can assume the work interaction to be negligible or no work interaction. So, W 2 3 is 0. What about Q 2 3? Condensation heat is being rejected. So, it is equal to Q c minus Q c because heat is being rejected by the system. Heat rejected by the system is negative. So, putting this minus Q c is equal to H 3 minus H 2, which gives Q c is equal to H 2 minus H 3. Finally, we have the pump process 3 to 4. So, Q 3 4 minus W 3 4 is equal to H 4 minus H 3. We are assuming isentropic process in the pump. So, we have Q 3 4 to be equal to 0 and what about W 3 4? There is work interaction, the magnitude of which is the pump work and it is positive or negative. Here work is being done on the system. So, it is negative. So, we have plus W p to be equal to H 4 minus H 3. Let us drop the plus sign. So, we have obtained all the 4 interactions that are required. Then the net heat interaction Q net or the cyclic integral of del Q should be equal to Q b minus Q c. Now, if we refer to the previous slide again, here our Q b was H 1 minus H 4 and Q c was H 2 minus H 3. So, it is H 1 minus H 4 minus H 2 minus H 3. This is the net heat interaction. The net work interaction should be equal to the net work output from the turbine minus net work consumed during compression in the pump, which we are calling the pump work. So, here W t is H 1 minus H 2 and W p is H 4 minus H 3. So, H 1 minus H 2 minus H 4 minus H 3, and if we just reorient these two, then we can easily write this as H 1 minus H 4 minus H 2 minus H 3, which is the cyclic integral of del Q. Of course, it is satisfying the first law of thermodynamics, which is definitely very logical. Now, how to get the thermal efficiency? The thermal efficiency for this cycle should be equal to the net output by the heat given to the boiler, that is 1 minus Q c by Q b or if we are interested only in terms of W net by QB, then we can write this as WT minus WP by QB. If we keep on following the letter convention, then what is your WT minus WP? As we have just written, it is H1 minus H2 minus H4 minus H3, and QB is H1 minus H4. Occasionally, we can reorient this term as something like this. H1 minus H4 we are writing as H1 minus H3 minus H4 minus H3. What is H4 minus H3? H4 minus H3 is the pump work. Now, how to get the pump work? Of course, the pump work is equal to H4 minus H3 that we have seen earlier, but there is a different way of calculating this one also. We know that it can be written as U plus P4 V4 minus U plus P3 V3 this. Now, as we are talking about a liquid, during this particular process its changes in internal energy, as we are talking about an isentropic process during which, okay, I would like request you to refer back to one of our earlier discussion, probably in the very first module, where we mentioned that if we are talking about an isentropic process for an incompressible substance, that will also remain isothermal. Can you remember that we have proved that for an for an incompressible substance, an isentropic process is also isothermal, and if that is isothermal, then that actually will lead to with no change in the internal energy. So, this thing basically refers to the changes in the flow work part. Now, again, as we are talking about a liquid which is having extremely small changes in its specific volume, then this can be written as V into delta P, or change in V, or in this particular situation it is the specific volume of the liquid into boiler pressure minus the condenser pressure. This is generally the way, though we can easily calculate the pump work as H4 minus H3, but quite often we would like to go for this as the specific volume into PB minus PC, because the specific volume, as long as the change in specific volume between state 3 and 4 are negligible, then we can just blindly go for the change in pressure multiplied by the specific volume as the pump work, and this pump work magnitude often is extremely small compared to the turbine work. So, if we neglect the pump work, then this efficiency expression comes out to be H1 minus H2 upon H1 minus H3, which of course is neglecting the pump work. So, this is the way we can calculate the thermal efficiency. There are a couple of other terms that are quite often used in conjunction with any power cycle, particularly in conjunction with the vapor based power cycle. One term that we have used in the previous week also, which is the back work ratio. Back work ratio is nothing but the pump work divided by the turbine work. And this back work was quite significant in case of gas turbine, but it is expected to be much smaller in this case. We also can define an work ratio, which is the net work output divided by the gross production, which is the turbine work. So, W net by WT, again this one also we have used in the previous week. Another term quite commonly used for giving the specifications of power stations, that is called the specific steam consumption, or SSC. It refers to the amount of steam consumed to produce unit power output. That is, if m dot is the mass flow rate, and then the amount of mass flow rate of steam required to produce unit power output, that is m dot divided by m dot into W net, which is of course the power output that we can get, and therefore, it is just nothing but 1 into W net. So, what will be the dimension or SI unit of this quantity? It is 1 upon W net. So, its unit will be kg per kilojoule. Quite often this is extremely small. So, what we do is we represent SSC as 3600 by W net as kg per kilowatt hour by multiplying with 1 hour, that is 3600 seconds. Now, here whatever analysis that we have done, that is assuming an ideal cycle, that is no irreversibilities, but practically as we have seen for gas turbines, we can have irreversibilities during both expansion and compression processes. Just shown here, if we have isentropic expansion, then we should have reached point 2s, but because of the presence of the irreversibility, we have actually reached point number 2. Similarly, in the pump, if there is no irreversibility, we should have reached 4s, but because of the presence of irreversibility, we have reached point number 4. So, here also we can define isentropic efficiencies. What will be the isentropic efficiency for the turbine? That is the actual work output divided by ideal possible work output. So, it will be H1 minus H2 by H1 minus H2s. Similarly, the isentropic efficiency for the pump will be ideal work input requirement by actual work input requirement, because it is a work producing it is a work consuming device, and least work consumption will correspond to the ideal process, that is the fully reversible process. So, because of the presence of irreversibilities, more work input will be required. So, the isentropic efficiency for the pump will be the ideal work input requirement, which is H4s minus H3 by actual work input requirement, which is H4 minus H3. The effect of both these isentropic efficiencies are to cause a reduction in the final output from the system. Let us solve one numerical example now to test whatever we have learned so far. A steam power plant operates between a boiler pressure of 40 bar and a condenser pressure of 0.03 bar. It is not mentioned specifically, but we are assuming an wet cycle, that is the exit state at the, or I should say the state of steam at the exit of boiler or inlet to the turbine is that of saturated vapor, not superheated. So, we have to calculate the cycle efficiency of specific steam consumption for 3 different conditions. First, for a Carnot cycle using wet steam, then a Rankine cycle with saturated steam at the entry to turbine, so basically wet steam, and third the same Rankine cycle with 80% isentropic efficiency for the turbine. Nothing is given for the pump, so you can assume pump to be ideal, but turbine has an isentropic efficiency of 80%. Let us solve the first part, which is for a Carnot cycle. So, this is the diagram. Here your pressures are 40 bar and 0.03 bar. Then what will be these two temperatures? The highest temperature TH and the lowest temperature TL. How can you identify this? Remember, as the phase change process 1 to 2 which corresponds to this 40 bar pressure and this temperature TH, this is a phase change process. So, pressure and temperature both should remain constant and they should correspond to each other. And so, the temperature this TH, which is in this case is equal to T1 and T2, should be equal to T sat corresponding to this boiler pressure, which is 40 bar, and I have pre-calculated the number, or actually I have used the data table which we have used earlier also. From the table we are writing this to be equal to 250.35 degrees Celsius, and if required we can convert to absolute temperature also, 523.5 Kelvin. Similarly, the lowest temperature is T3 to be equal to T4, which is the saturation temperature corresponding to the condenser pressure 0.03 bar. Here the boiler pressure is 40 bar and condenser pressure is 0.03 bar. Whatever data table you are using, be careful about the units. Quite often the tables give the data in terms of kilopascal or megapascal or maybe in bar. The table that you are using, which unit is followed, be very careful about that. So, from the table that I am using, this is 24.68 degrees Celsius, which gives to 297.83 Kelvin. We know the highest and lowest temperature. Can we calculate the efficiency? Surely we can. The Carnot efficiency in this case is 1 minus TL upon TH. So, putting the number, it will be coming something like 43.11%. So, this is the first answer that we are looking for, but this is the way we can always calculate the efficiency, but we shall be calculating it again using the heat and work interactions. So, let us try to locate the points. H1, what it will be, what this one will be? H1 is located on the saturated liquid line. So, it should be HF corresponding to the boiler pressure, and it is coming as 1087.4 kilojoule per kg. S1 the same way, SF corresponding to the boiler pressure. So, it is coming to be 2.7966 kilojoule per kg Kelvin. Whatever data table that you are using, please keep on doing it parallel to me and use your own values. What about H2? Point 2 is located on the saturated vapor line. So, H2 should be equal to Hg corresponding to the boiler pressure, which is in my table, this is the value. Similarly, S2 is equal to Sg corresponding to the boiler pressure, which is 6.0696 kilojoule per kg Kelvin. So, we have got the information for point 1 and 2 and that we have noted. If we expand these lines, vertical lines, then this is your S2, which should be equal to S3, and this is equal to S1, which should be equal to S4, because 2 to 3 and 4 to 1 are isentropic processes. And this is the information that will allow us to allocate the point 3 and 4. We know their pressure or temperature, and now we know their entropies also. Then let us try to calculate S3. S2 is equal to S3, then it should be what? S3 is located on the condenser pressure. So, the value of S3 should be equal to SF corresponding to the condenser pressure plus X3 into SFG corresponding to the condenser pressure. That is, your X3 should now be equal to S3 minus SF corresponding to the condenser pressure by SFG, or SFG is nothing but Sg minus SF. So, for corresponding to the condenser pressure, you check the table, get the values of SF and Sg or SFG, and your X3 will be coming to be 0.6951. Look at that, such low value of quality at the exit of the turbine, only in the range of 70%, which is extremely low and will lead to large amount of corrosion or erosion, I should say. Corrosion is associated with chemicals, erosion is associated with steam. So, significant amount of erosion can take place here, as I have mentioned earlier. Now, look at point 4, we know that S1 is equal to S4. So, the same way it is equal to SF corresponding to the condenser pressure plus X4 into SFG corresponding to the condenser pressure. From there, X4 is equal to S4 minus SF corresponding to the condenser pressure by SFG corresponding to the condenser pressure, and putting this, your X4 is coming in this example 0.2971. You please recheck all these calculations, because I may have done some calculation mistake, it is possible. I have done quite hurriedly and I have not rechecked the numbers. So, you please do them again. Once we have this X3 and X4, then you can calculate H3 and H4. Your H3 will be equal to HF corresponding to the condenser pressure plus X3 into HFG corresponding to the condenser pressure, and that H3 will be coming, you have to get the values of HF and Hg corresponding to the condenser pressure from your table. So, it is coming 1799.73 kilojoule per kg. Similarly, H4 will be equal to HF plus X4 into HFG, both correspond to the condenser pressure, and this value of H4 I have not noted actually. Okay, you please calculate the number whatever you are getting, because I have not noted the value of H4. Yes. Now, using these values, what information you can get? QB, the heat added to the boiler, what that one should be equal to as per this diagram. This should be equal to H2 minus H1. You have H1 and H2. From there, we are getting the QB to be 1713.4 740 kilojoule per kg. Here of course all calculations we are doing for per unit mass flow rate. So, we are having this kilojoule per kg as the unit. Then Q and the QC, how you can calculate? Okay, H4 you can easily calculate, but there is another way you can calculate QC also. What is that? You know X3 and X4, then what will be your QC? QC will be equal to H3 minus H4, and you have the relations for H3 and H4 which you have just used. So, from there can't we write this as X3 minus X4 into HFG corresponding to the condenser pressure? So, this QC is in this particular case is equal to 972.67 kilojoule per kg. WT, the turbine work, is H2 minus H3. So, the turbine work is coming to be equal to 1001.07 kilojoule per kg. So, you have calculated the turbine work, and similarly the pump work also we can easily calculate. The pump work will be equal to H1 minus H4. I forgot to note the value of H4. In this case it is coming to be equal to 260.34. So, you have got all the 4 calculations, all the 4 parameters that we need. So, can you recalculate the efficiency again? Your thermal efficiency will be equal to one minus QC by QB, or it can be equal to W net by QB. Whatever way you calculate, that will come as the same 43.11%, or maybe just small change in the fraction. And the specific steam consumption is 1 by W net. Now, what is your W net in this case? W net is WT minus WP. So, if we calculate, your W net will be coming as 740.73 kilojoule per kg. That gives a specific steam consumption of 4.86 kg per kilowatt hour. So, this is the other answer that we are looking for. So, note these numbers. Now, we shall be comparing them with a Rankine cycle, an ideal Rankine cycle. This is a Rankine cycle for which we have to do the calculation. Look at this, state number 1 and 2 are the same, state 5 that is shown here, that is similar to this particular state. So, the state 1, that is state at the entry and exit of the turbine, are same, but the change is at the end of condensation process. Here the condensation is not stopping somewhere in between, rather it is being extended up to the saturated liquid point. Of course, I have got a different diagram, so the indexing are a bit different. Just I am borrowing the values from the previous problem. Accordingly, I can write H1 in this case to be equal to 2800.8 kilojoule per kg. H2 in this case will be equal to 1799.73 kilojoule per kg, and H3, that is a new point coming in. Now, what will be the enthalpy there? H3 definitely is a saturated liquid, so it is HF corresponding to the PC. So, very easy to get this, it is 100.98 kilojoule per kg. H1 and H2, that difference is going to give you the turbine work, that is H1 minus H2, which remains the same as in the previous case, 1001.07. So, the turbine work remains the same on adoption of the Rankine cycle, but what about the pump work? The pump work definitely will be changing. So, let us try to calculate the pump work. The pump work in this case will be equal to the corresponding specific volume into the boiler pressure minus condenser pressure. Now, check the value of this specific volume. Let us say it put is V3. V3 will be equal to V4, which is equal to Vf corresponding to the condenser pressure. These two should be very nearly equal to each other, and if you put the values, then you will get this maybe something like 0.001 meter cube per kg, extremely small number that we get, and V3 and V4 remains virtually the same, and putting that we get the pump work to be equal to 39.97. So, the pump work is coming as 39.97. Just go back to the previous case. Turbine work is the same, pump work was 260. How much reduction that we are getting? Simply by expanding the condensation up to the saturated liquid line, this pump work has reduced to such level this. And so, your net work output, that is Wt minus Wp, that now comes to be equal to 961.1. So, in the previous case it was in the range of 740, now such a drastic increase. So, the total work output, that is definitely increasing, and from there we can calculate the specific steam consumption, that is 1 by W net, which will be coming to be equal to 3.74 roughly kg per kilowatt hour. So, the specific steam consumption has decreased because we are getting larger amount of work output. But what about the efficiency? Work output is increasing, so efficiency will increase, but again we know that Carnot cycle gives us the highest possible efficiency. Then to calculate the efficiency, we need to check the heat input requirement also. Now, heat input requirement here, the QB is equal to H1 minus H4, and what is your H4? H4 can be written as H3 plus the pump work. So, putting, we have already got H1, we have got H3, we have got the calculate the pump work. So, putting this, your QB in this case will be coming as 2659.85. Now, compare this one the previous case. Here it was significantly lower. So, the work output, net work output was lower, but the heat input requirement was also much lower, where we are getting higher work output, but at the cost of increased heat load. So, the thermal efficiency in this case will be equal to W net divided by QB, and if you put the numbers, it will be coming in the range of 36.13%. In the previous case with the Carnot cycle, we had efficiency of about 43%, so 7% reduction in the thermal efficiency because of the conversion from Carnot cycle to the Rankine cycle. Now, the third part of the problem, where we are having an isentropic efficiency, so irreversibility is in the turbine, so some further loss, which is the situation something like this. We do not have irreversibilities in the pump side, but in the condenser side. So, we have to calculate the pump work. Now, eta T, we know that will be equal to W actual by W isentropic, which is the Wt that we are using so far. So, your W actual will be equal to your eta T into the isentropic work that we are getting. So, that is 0.8 rather into the previous case the work output that we have got, assuming ideal cycle. So, it will be coming something in the range of 800.86 kilojoule per kg. Rest of things will remain the same. So, accordingly the net work output, as pump side there is no change. So, net output will be just W actual minus the same amount of pump work, which gives a value of 760.88 kilojoule per kg. 0.4 is the same, location of the 0.4 is the same. So, and location of 0.1 is also the same. So, QB, which is H1 minus H4, that will also remain the same. So, accordingly your thermal efficiency will be equal to the new value of net work output by the earlier existing value of the boiler work or boiler heat input requirement, and the efficiency will be coming in the range of 28.61%, and the specific steam consumption will be the reciprocal of this net work output. So, that is coming to be equal to 4.73 kg per kilowatt hour. So, an increase in the specific steam consumption as well. I would request you to repeat the same problem by assuming an 80% isentropic efficiency on both boiler and turbine side and see what will be the final calculation. But this I am sure has demonstrated you amply about how to do the calculation. Next we move to the more realistic Rankine cycle, where instead of wet steam we go to the superheated steam. Just look at the diagram. Here the heating in the boiler has not stopped at point 6, rather we have extended this to point number 1, which is on the superheated side. And then once we are expanding this, then at the end of expansion, either we can as shown in the diagram, we can go to the saturated vapor state, or even if we are entering the mixture, we can maintain a very high quality mixture, so that we do not have to bother too much about the erosion related problem. Look at the diagram here. The liquid, high pressure liquid that is coming out of the pump, that goes through this series of heat exchangers where it is heated up to saturated mixture state, that is state number 6. Then we supply it to a boiler drum. In the drum, the liquid and vapor phases are separated, and it is only the vapor phase that passes to another series of heat exchanger, which is called the superheater, where it is heated up to the final temperature. So, this is the way generally the Rankine cycle are used in practice, where instead of stopping with the wet steam or saturated steam, we go to the superheated steam in an effort to extract some more work output. Just look at this TS diagram, you can clearly see that the total area enclosed by the diagram is larger. So, total heat interaction will be more, total work interaction also will be more. So, the total output that we are going to get from the superheated steam or Rankine cycle with superheated steam definitely will be more compared to the previous case, but your heat interaction or heat input requirement, that is also more. Just try this numerical problem. The same cycle, we have the same boiler pressure of 40 bar and condenser pressure of 0.03 bar, but here there is a typing error. You have to calculate the cycle efficiency and specific steam consumption for Rankine cycle. Just remove this part where the steam is superheated to 500 degree Celsius. Here the steam has been superheated to 500 degree Celsius. So, your H1 corresponds to a situation where your pressure is 40 bar and temperature is 500 degree Celsius. It is superheated, this temperature is well above the critical temperature. So, once we are go for the superheating, one of the earlier problems that I have mentioned, we are restricted by the critical temperature limit, that is no more applicable, because we are doing the phase change at a temperature lower than critical, then we are taking the vapor phase and then heating up to a higher temperature, so that we can go to much higher temperature limit. So, to solve this, you have to use the superheated vapor table. These numbers will be coming as 3485.5 kilojoule per kg, and your S1 entropy at the same state is 8.1933 kilojoule per kg Kelvin. Now, using this S1 and the ideal cycle, you have to compare the exit state of the turbine. In ideal scenario, we know that S2 is equal to S1, and this S2 we have to check now. S2 corresponds to a pressure of 0.03 bar. If this S2 is greater than SF corresponding to this, we are in the mixer part, and if this is greater than Sg, then we are still in the superheated part. But in this situation, if you do the calculation or if you check the table, then you will find that your S2 is restricted between SF corresponding to PC and Sg corresponding to PC, which shows that S2 is on the mixer side. So, we can easily calculate X2. X2 will be equal to S2 minus SF corresponding to the condenser pressure by SFG, and your X2 will be coming to be equal to 0.9533. See, such high value of quality we are getting, 95%. So, we do not have to bother about the erosion problem. H3 or H2 rather will be equal to HF corresponding to the condenser pressure plus X2 into the latent heat corresponding to the condensation pressure, to be equal to 2430.75 kilojoule per kg. So, the turbine work is equal to H1 minus H2, that is equal to 1054.75, which is definitely higher than the previous case. The pump work remains the same that we had, because pump size information we have not changed. So, the pump work was 39.97, from where we get the net work output to be equal to the turbine work minus pump work to be equal to 1014.78, and the QB also will remain same. Okay, we have to identify the location of the H4, which is the exit of the pump. From there we can have to identify the heat required in the boiler as H1 minus H4, and from there we can calculate the thermal efficiency. I am leaving the calculations to you, just check the final answer, which is W net by QB. In this case it will be coming to be equal to 30.34%. And if you are able to locate the points properly, your QB will be equal to 3344, something like this, sorry, 3349.03 kilojoule per kg, and your specific steam consumption will be coming as 3.547 kg per kilowatt hour. So, this problem has demonstrated you the use of Rankine cycle with superheated steam at the boiler exit. So, that is it for today. The deviations in the actual cycle I have already talked about. As we have mentioned, we can have isentropic efficiency for turbine and also for the pump, and we can also have pressure losses in the boilers and condensers as shown in this diagram. Because of the pressure losses, the pressure at the exit of the boiler and at the exit of the at the entry of the boiler and the exit of the boiler may not be the same. Similarly, the pressure at the exit of the condenser may be much lower than at the entry to the condenser. So, in real cycle we have to be careful about these deviations also. So, today we have talked about the vapor power cycle. First we talked about the Carnot cycle and we explained why the Carnot cycle is not possible to achieve in practical operation. Then we mentioned about the Rankine cycle. First we analyzed it assuming wet steam, that is saturated vapor at the entry to the turbine, and then superheated vapor at the entry to the turbine. So, that is it for the day. In the next class we shall be talking about the factors on which the efficiency of the Rankine cycle depends, and then the options of improving the efficiency of the Rankine cycle. Till then, go through this lecture, try to solve a few more problems and grasp the concept. Thank you.